Thank you so much for being here. I'm Nick Erickson, your host for today's webinar. I'm joined by Casey Willis, product manager for strain measurement devices at Instron, where she leads the extensometry portfolio, including clip-ons, automatic contacting, and video extensometers. We're also joined by Josh Campbell, a member of the technical staff at Covalent, an independent materials testing lab based in Silicon Valley. In today's session, Casey's going to walk us through the extensometer landscape from classification standards to real-world application matching, including the differences between contacting types like clip-ons and automatic contacting, and contrasting those to non-contacting video extensometers. So whether you're evaluating your current setup or exploring new technologies, this session should leave you with a clearer sense of the options out there and what to consider as you think through the best fit for your lab. We're going to hear from Josh, who will share Covalent's experience using the Instron AVE3 video extensometer, including some examples from testing thin films and foils used in battery production. Covalent was actually one of the earliest labs to adopt the AV3, which we launched over a year ago. So Josh brings a good amount of hands-on time with the device. We're expecting the presentation should take around 45 to 50 minutes, followed by Q&A. Please feel free to submit those at any point using the Q&A panel. And I'd also like to note that this session is being recorded. You'll receive an email afterwards with a link to that recording, and it'll also be available on our website at instron.com. So with all that said, let's get started. Casey, over to you.
Thanks, Nick. I'll get my screen shared. There we go. Hi, everybody. Thanks for joining today. My name is Casey Willis, and I am the product manager at Instron. Prior to managing the strain portfolio, I was an applications engineer, and in that role, customers would frequently seek our advice in the extensometer selection process. So the goal of this webinar is to make this selection process a little bit easier. On the agenda today, we'll go over the fundamentals of extensometers, then we'll dive into the types of extensometers, those being contacting or non-contacting types, and the pros and cons associated with each of those. Then we'll spend some time diving into each of the types of extensometers specifically. We'll wrap up with what factors go into that final selection process. And then we'll end with a customer spotlight to hear firsthand what it's like choosing an extensometer. Before we jump in, let's just get an understanding of what an extensometer is. A quick little refresh. Extensometers come in all shapes and sizes. They're designed with the same goal in mind, and that is measuring material deformation. The principle of operation for extensometers is pretty simple. You have your initial gauge length set. You can see
Hey,
it in the image above.
hey, Casey.
Yep.
Can you actually? I'm not sure if can you double check, make sure you're sharing your screen?
Can we see that now?
Yes,
I see
perfect.
that.
Okay, perfect. Um, so back to when you're setting up your extensometer, you're going to choose an initial gauge length and get that set. So as your specimen begins to deform, that delta L that we call out on the slide, that's the change in length. And this can either be measured physically or virtually. For physical measurement, that deformation is translated into an electrical signal. That signal is then output to your test frame or controller, and it will get translated into the stress strain data that you see from your frame in your software, those curves that are generated. So being able to obtain very highly accurate strain measurements is critical for the material selection process. How a material behaves under load will govern what situations it's appropriate to be used in and implemented in. Extensometers are the most accurate way to metric strain. The test frame that you're using is certainly capable of tracking displacement from its crosshead, and that displacement could be used to calculate strain if you wanted. However, there is some nuance to this. Your frame is likely outfitted with grips. Maybe it has pull rods. Maybe there's adapters. Each of those connections introduce an additional amount of compliance into your load string. So when your test starts and you apply a load to your specimen, that load is being translated through your load string. So it's also subject to some deformation. So your test frame, if you're looking at crosshead displacement, won't be able to identify the deformation that's coming purely from the specimen versus the grips and fixtures that you're using. International standards bodies like ASTM and ISO recognize that this is an industry-wide challenge and often recommend or require extensometers be used for certain material property, measurements, or applications. The level of accuracy that your extensometer needs to meet can change depending on your standard and your specimen geometry. I have some common examples of test standards from metals, plastics, and composites customers that you can see listed out on the slide. And as best practice, I highly recommend you check your standard annually that you're testing to ensure you're using the latest version. Each of these committees will meet to edit, revise, add annexes, change descriptive language. So you need to make sure you're doing your due diligence and using the most up-to-date standard revision that they offer. If your testing standard requires an extensometer, it's likely pointing to ASTM E83 or ISO 9513. These standards outline how to classify and verify the performance of extensometers. They both specify accuracy limits based on relative and fixed errors to ensure you're getting a very reliable yield strength and modulus of result. Both standards require extensometers to meet a specified error threshold across a measuring range. Major difference between these, ASTM E83 uses letter-based classifications and ISO uses number-based. Each of these standards bodies, I listed out the slide in order from most accurate to least accurate. In general, the higher classifications are often required for specimens that exhibit lower percent strain, like composites or metals. And as you work your way down that list, those are often the classifications, the minimum requirements for testing higher elongation materials like plastics or elastomers. Before we dive into each of the common types of extensometers, I did want to note just an obvious but very important difference between these two main types of extensometers. On the left, you'll see some examples of contacting extensometers. These measure strain by physically touching the specimen. Within this bucket, there's a spectrum of automation. You can have an extensometer that you need to attach or adhere onto the specimen, or you can have something more automated that will handle the attachment itself. Then on the right side of the slide, you'll see an example of non-contacting extensometry. The name itself, pretty explanatory. There is no physical contact with the specimen. The extensometer works by tracking marks on the specimen through space. Now we're going to get into the overviews of each of the specific types of extensometry from these two buckets. We're going to start with non-contacting. We're actually going to start with contacting and then work our way with non-contacting. Kicking off the contacting bucket, we're going to start with strain gauges. Strain gauges are thin resistive foil sensors bonded directly to a specimen with an adhesive. So as your material deforms, that foil is going to stretch. And that change will actually change the electrical resistance of that gauge. And that deformation will be converted into strain values. So cure times for adhering these foils can be either minutes or hours, depending on what material and adhesive you use, the surface prep that you did for your specimen, and the bonding method that you're going to be using. I typically see composites customer using strain gauges or customers testing specimens with complex or irregular geometries. Strain gauges are great because they're extremely precise and can be really helpful in niche applications. Certain gauges and adhesives can even withstand extreme elevated or subambient temperatures, where traditional extensometers would just not be able to function at those temperatures. A common customer complaint I hear with strain gauges is setup time. Each gauge needs to be adhered individually. Certain adhesives, especially for those non-ambient tests, may have cure times of a few hours, so it's certainly not ideal for a high throughput lab environment. Also, keep in mind these are consumable and need to be disposed of after the test is complete. One last thing I'll say about strain gauges before we move on is there is an element of human error to them. So the possibility of misalignment, improper attachment, that's always a risk. And any potential mistakes in this area could translate into measurement error. So that's just something to keep in mind if you are using this method for strain measurement. Following the evolution of this technology, the next step up from a consumable gauge would be a clip-on. So clip-on extensometers are reusable mechanical devices that clamp onto a specimen at a fixed gauge length. They have two knife edges that will contact the surface of your specimen, and as that specimen deforms, that movement is translated to a strain gauge or LVDT sensor inside of that extensometer body. That sensor will convert displacement into strain. We have some examples on the left side of the screen. You can see that clip-ons come in a variety of different sizes. The top image is a clip-on that accommodates a 50 millimeter gauge length, while the bottom image accommodates a smaller 25 millimeter gauge length. Though our gauge lengths are fixed, there is some flexibility within your single device. The clips that are holding the specimen to the knife edges, those little pieces of metal that are protruding from the images, those can be swapped out and changed to accommodate a range of specimen thicknesses or diameter. In general, clip-ons are one size fits one application. So when I visit customers that offer centralized testing services, I'll typically see a shelf or a cabinet filled with clip-ons. They might need to stock a 75 millimeter clip-on for plastics testing. They might need to have an averaging transverse clip-on for sheet metal testing. They may have to have a 50 millimeter axial for metallic rounds. Whatever you're testing, if your needs change and the demand changes, they often have to buy an extensometer to suit that application if it requires a different gauge length. So if you're considering a clip-on, I would ask yourself a few questions. First off, what material are you testing? If the specimen's soft, the knife edges may dig into the specimen. Is your specimen really thin? Can it hold the weight of a clip-on? The last thing that you want is your clip-on causing premature failure or skewing your results. Question number 2, you should ask yourself, who's attaching the clip-on? You want to make sure that your operator is comfortable attaching the devices and understands the importance of alignment during testing. It is not uncommon to see a clip-on slightly tilted when it's attached. Accidents happen, but those mistakes can throw off modulus calculations and leave your team wondering what happened with this test. It's just not explainable. Question number 3, how does your specimen fail? If you are testing something like a composite, those exhibit very violent and explosive failures. So you run the risk of jostling around those very sensitive electronics inside the extensometer when your clip-on is holding on to the specimen through failure. So that might not be the best case scenario and best situation to be using clip-ons in if they're going to be subject to those types of forces repeatedly. The last non-automated device that I'll cover is the long travel extensometer. The long travel extensometer is a contact-based device specifically designed for rubbers, elastomers, or any other high elongation material. Unlike standard clip-ons, it features a dramatically extended range, and it's capable of measuring strains well beyond 100% elongation. The knife edges are actually contoured to grip soft surfaces, so they won't be cutting in or damaging the specimen like traditional clip-ons would. It's a fairly straightforward device designed for measurements in the axial direction, and it does require manual attachment prior to testing. But overall, basic device for the basic requirements of our elastomers customers. Unlike the long travel, the AutoX, our automatic contacting extensometer, is designed to eliminate the need for operator involvement in the attachment and removal process. It has motorized arms that will position themselves to the specified gauge length that you set in the software. It'll automatically apply the knife edges to the specimen surface. You can see in the images on the left that there are knobs on the sides of the arms. Those are adjustable, so you can either increase or decrease the tension to best suit the material that you're testing. Your initial gauge length is set in your software and can be changed or adjusted anytime. The knife edges that actually are making contact with your specimen are also interchangeable depending on whether you're testing flat or round specimens. In the bottom image, you can see that there's also a transverse module option. Oftentimes, customers needing to calculate R value will include this when purchasing an AutoX. Since the AutoX is a more automated solution, it's typically sold onto automation systems or QC in lab environments where throughput and repeatability are critical. A shortcoming of the AutoX is a limitation that you've heard in the previous slides. This is a contacting device and it falls in that contacting bucket. And that means that components like those knife edges are consumable over time. These are cheap and easy enough to replace, but that does mean occasionally your operator should be checking these to ensure your testing equipment is functioning properly. If your knife edge is dull too much, you may notice slippage in your graph. So this is just something to be aware of. There might be some preventative maintenance that you need to stay on top of with this. If minimizing the hassle of preventative maintenance sounds appealing, or you need a more flexible extensometer option that will not only cover your testing requirements today, but applications that might get thrown your way in the future, then I'd recommend a non-contacting extensometer. So the advanced video extensometer, or the AVE, is a video-based extensometer that measures strain by tracking marks on the specimen surface. It can be configured to cover a wide range of specimen gauge lengths and elongations, and it's a great alternative to purchasing and maintaining multiple clip-on devices because it has the ability to consolidate all of those applications into one device. Applications from sub-sized metallic specimens to high elongation rubbers can be covered in one device, unlike clip-ons where you're probably going to have to stock at least two to accommodate that range of testing. When you kick off a test with the AVE, the device will automatically detect the gauge length that you've marked at the start of the test, and it will track that through failure. So this feature could be a nice alternative in those risky situations like composites testing, where if you were using a clip-on, you'd need to retrieve that device while the specimen's still under load. A non-contacting option eliminates that safety risk and prevents you from having to go back into the inactive load string to get your device. Removing the need to retrieve the device and the ability to track through failure is also helpful for customers testing in chambers. You can just let the test run its course. You don't have to deal with opening the chamber door, putting on your gloves, retrieving that clip-on, closing the door. It's just a much more streamlined workflow. Being a video-based platform, there is more flexible options for analyzing those live images that your device is pulling in. You can track axial strain, you can track single point transverse, or you can configure the device to measure and average multiple points in the transverse direction. And this is often our recommendation for sheet metal customers because it can greatly decrease your coefficient of variation when you're trying to determine R value. If you want to take this analysis one step further. Using digital image correlation, a full field strain map can be generated after a test, and that can be synchronized back with your data from Blue Hill Universal. Oftentimes, I see this in research and development environments, and DIC just acts as a really powerful tool to help labs understand what's happening in various regions of the specimen during a test, aside from maybe just what you see with single point axial tracking traditionally. One limitation that I do want to expand on is testing in a chamber. So this isn't exactly a limitation of the AVE, it's really an application limitation. In extreme subambient temperatures, ice will begin to form on your chamber window. If you've ever gotten in the car on a very cold day and had ice on your windshield, you need to defrost your windshield before you start driving so you can see. Video extensometers need to see like us to function. So you need to make sure if there is humidity in your lab, that is your window fogging up and freezing over? Because if that's the case, then our recommendation in that situation would to be to use a contacting extensometer like a clip-on, because you really want to make sure that you're not compromising your data collection in those situations. To quickly just summarize everything we talked about, being able to choose the right extensometer for your lab will be easy. You ultimately are the most familiar with what's important to you and your team, but you should always keep in mind these three things. One, your application requirement. What standards are you trying to comply with? Have they been updated this year? Always check that. And what classification of extensometers do they call for? Number two, what do your specimens look like? This may immediately narrow down the number of extensometers that you're choosing from. For example, a thin film can't withstand the weight of a clip-on, so in this situation, a non-contacting option is preferred. Number three, what are your expectations for throughput and repeatability? If added time of attaching and removing devices from your specimen is going to slow down your lab, then you should be considering a more automated solution. If there are questions or points of clarification that you'd like to talk through, your sales engineer and our applications team are great resources that I can connect you with. These are the folks that attend those ASTM and ISO meetings regularly every year and live day to day supporting our customers in their testing efforts. So chances are the question that you have, they've likely already answered. Now I'm going to hand it off to Josh Campbell from Covalent. I'll let him introduce himself when I turn things over, but Josh's team recently purchased an AVE from Instron, and we'd like to give them the floor to showcase how they're using the device and some of the interesting testing that they're doing at Covalent in California.
Thank you. Thank you very much, Casey, Nick. I appreciate the opportunity to be here. Just briefly, Covalent is an analytical services lab in Sunnyvale, California. We're here a little bit earlier than some folks that are hosting on the East Coast. As Casey said, we're going to talk about our implementation of the AVE3. Try and share my screen here. And there. Uh, okay, so I work with, I'm a member of the technical staff here at Covalent. I do mechanical testing in addition to all the good work that I get to do on our Instron. I also do work in rheology, indentation, dynamic mechanical analysis, and I'm starting to do a little bit of work in analysis of thermal properties. That's who I am. I do want to briefly introduce our company. On the screen are kind of three high-level things that we want our customers to know about the services we provide. We do want to be your trusted partner. We want to provide convenient access to metrology and analytical services. And although that field and industry has been around for a while. We're constantly working to try to improve on how that whole service is provided and how we deliver the results, the quality, the speed. We put our customers first. We want to deliver faster, more impactful materials and analysis to support R&D or any type of quality issues our customers may have. And to make sure that we or you can be confident that we're giving you high quality results, we do have ISO accreditation. On this slide, talks a little bit about more about us as a company, where we're at in our growth, who we are, and who we work with. Covalent is the high growth innovation leader in outsourced analytical services. In terms of revenue, in 2025, we had $25 million in revenue, which was 20% growth, and we're continuing to accelerate our growth in 2026. We have high expertise staff, 85 employees, 30 of which have advanced technical degrees. We work with the highest tech customers in all industries, about 550 different customers per year, coming from 30+ different industry segments. To make sure that we can provide the best equipment and analytical services, we develop partnerships with manufacturers of analytical instruments. So we currently have 12 active partnerships. That helps us to ensure that we're giving you the leading equipment technology and the support to run that equipment to its highest capabilities. However, no lab is going to have every piece of equipment that exists. And so for the things that we don't offer internally, we have a network of, at this point, over 500 partners that we work with globally. So whatever type of analytical service measurement you need, you can come to Covalent and we can provide that to you. This slide shows the different analytical service categories. I'm just going to touch on each of these at the high level, but it should give you a little idea of our breadth. We offer electron microscopy, X-ray characterization, optical imaging and analysis, analytical chemistry, material property testing, and particle analysis. So a very broad range. So that's who Covalent is. Now I want to talk about our implementation of the AVE3. So we want to be able to service any customer that comes to our door. So the challenge is that we want to, as the slide says, provide mechanical testing services to customers spanning the full range of industries and the full range of material applications and products. So what that means is that anything that has mechanical requirements that can be contained in a product or used to produce a product, we want to be able to provide mechanical testing services. That's a pretty broad range. No single piece of equipment is going to do all that. But from an extensometry perspective, we have found that the AVE3 is a single system that can cover quite a broad range. And so we installed this instrument in the third quarter of 2025, and we've had about a year working with it, doing projects. This slide gives kind of highlights in some detail the different types of applications we've studied. Obviously, we do standardized test samples, tensile dog bones. You can see in the figure on the right there some polymer tensile dog bones for tested under ASTM D638, both before and after testing. We've tested thin films, and I'm going to provide some specific data showing some of our thin film testing, which highlights the quality of output we get from the extensometer. In addition to standardized test samples, we also have done quite a bit of work with non-standard test samples. This typically would come about from a failure analysis investigation where some part has failed or not met requirements in some way, or maybe it's a quality issue and we want to understand mechanical properties. And so we can extract, we can identify the way to extract custom tensile geometries, and the AVE3 is a great way to measure strain during testing those samples. One thing that we find is we're always being pushed on the small side of things. Everybody wants to test teeny tiny samples. And so to give a sense for what we've done with the AVE3, under sample dimensions on the slide, we've tested cross sections down to 2 millimeters by 3 millimeters. We've tested films that have been down to 12 microns thickness, and we've done testing with gauge lengths down to 4 millimeters. So AVE3 does a great job with small, but obviously it can handle big samples too. Everything I've just said is stuff that we've tested for customers and provided data. We also have some applications that we're working on developing at the bottom of the slide. We've done a little bit of work with biological materials, specifically tendons. We've tried to use fibers down to monofilaments of 7-micron diameter. And then we are also working, Casey talked a little bit about digital image correlation. We're looking to bring that online. The figure on the far right of the slide shows an example of a strip specimen for DIC where we apply a speckle pattern. Instead of tracking just a couple dots, the AVE3 monitors the evolution of that speckle pattern during the test to give you strain mapping over the whole surface. For a lab like us, an obvious option in the past would have been contact extensometry, because we do have quite a range of different sample sizes and geometries. So here, this slide just talks about what are the operational benefits that we see of the AVE3 as compared to that approach of a contact extensometer. The benefits start immediately with setting up the test. The calibration of this instrument is very rapid, just a minute or two. Basically, you mount a calibration plate, and that calibration plate is shown in the image. It's just an array of dots on a surface that you put in the load string and click a few buttons on Blue Hill, and the instrument calibrates itself. Also, this whole setup is quite a bit less operator variability. As Casey mentioned, you have to apply a couple dots onto the sample, and that's what the AVE3 tracks to monitor displacement. That's really the only thing that an operator has to do for each test specimen is apply those dots. It takes a little bit of time to get the art of getting the dot down without having excess paint or ink, but after a session or two, you can be very efficient at putting those dots on with a template that comes with the instrument. When we move into test execution, we do find improved precision. The marker dots that you place on the sample, the AVE3 measures that specific gauge length for each test specimen, so you're not operating with a nominal gauge length as a basis to calculate your strain. And again, as Casey kind of talked about a little bit, there's no need to stop your test when you have a high extension sample. There's nothing that has to be removed. And the Blue Hill software, if you have a very high extension sample, you can get to the point where those marker dots get beyond the field of view of the camera. When that happens, the Blue Hill software very seamlessly converts to using crosshead displacement as the basis for the strain signal. And I've been very impressed with how seamlessly that happens. Now I want to talk a little bit about a case study. The goal here is to kind of highlight the quality of data that we've received from this instrument. This is focusing on battery materials and specifically thin film materials. Our samples, as shown on the screen, we did a battery separator, a polymer film, 25 microns thick, and also an aluminum foil current collector, 12 microns thick. And just based on the delicate nature of these samples, totally incompatible with a contact extensometer. We did our testing on the Instron 68SC5 using the AVE3. And here, the key things that the AVE3 provides to us are the material properties that depend on accurate measurement of low strains. And so specifically the elastic modulus and the yield stress, and that's what I'm going to highlight. This slide shows the results for the polymer film. There's a lot of data here, but the key points, I'm not trying to explain the material behavior in detail, but again, the quality of the data we get from the AVE3. So in the upper left is the typical stress strain curve, tensile stress as a function of strain. As we all expect, you have at points of low stress, you have a near linear regime, which is elastic loading, and then eventually the sample will deform permanently. That's the definition of your yield stress. Key point here at the bottom of the curve, or excuse me, at the bottom of the slide is that the tensile curves are measured with high precision. To me, it's very impressive how much these curves overlay one another up to the point of the tensile strength. In terms of quantifying a little bit, the elastic modulus, the coefficient of variation, is 0.4%. So what that means is that the magnitude of the standard deviation is just 0.4% of the average value of the modulus. So very high precision measurement. In the case of yield stress for the polymer film, the coefficient of variation was only 4%, also still a very high precision measurement. This slide shows results for the aluminum foil. Very similar story. You can see that the stress strain curves overlay very impressively, very repeatable data set, with the elastic modulus coefficient of variation being 3.7% and the COV for the yield stress only 1.2%. So we were very happy with the quality of strain data coming from this instrument. So to just kind of summarize, we find that the AVE3 supports mechanical testing of a very large range of sample sizes, geometries, and loading configurations with just this one device. We don't have a cabinet of contact extensometers we need to dig through. We can accurately measure strain on thin, fragile, and non-standard specimens. We do feel we have reduced setup time and need for operator intervention. And as I just showed, we can deliver consistent, repeatable results. We can do that across a variety of different operators and different types of testing applications. So that's kind of how we feel and what our experience has been about the AVE3. I do want to give a little bit of a plug for Covalent at the bottom of the slide. If you're interested to know more about us, or contact us, please check out our website. There's email address there for general inquiries. If you want to talk more details on mechanical testings, reach out to me personally. Thank you for the opportunity.
All right. So at this stage, we can jump into some questions. So if anybody in the audience wants to take this opportunity to add some more questions, I know we got some already queued up that we can ask our presenters. So it looks like, Casey, this first one is for you. How does the software account for the dot elongation during the test?
If you remember the slide with the plastic specimen that Josh showed, I think that's a good visual example of that dot elongating during the test. The AVE's algorithm was designed to latch onto and track the centroid of the marks that you apply. A centroid is just the geometric center of a shape. We recognized that not all of the initial marks are perfectly symmetrical, and that's totally fine. That's why our engineering team went down the path of tracking the centroid, because we know as materials deform, so do their marks. So we wanted to make sure that we were sufficiently tracking this, and our algorithm was robust enough to handle the changes that your specimens go through when it's a dot into an oval at the end before it breaks.
All right. And I know we've got Valerie here from Covalent as well. Looks like she's got a question to ask here.
I do. I saw tendons on the application list, and I know there's all kinds of interesting applications for, fake tendons for knee replacements and things like that. And I'm so curious if the Instron team has ever seen applications like that. Is anyone stretching out tendon replacements?
Yes, we definitely do quite a lot in the biomed space. I'm not super particularly fond of watching these tests or handling these specimens. Most of the time, I would say we do get a part of the samples that we get in will be actual tendons. Some of them are artificial tendons. So we definitely do see this. And it's not just tendons, it'll be different like muscle tissues, different aspects or stints that go into organs. So it's definitely a very widespread um, set of applications that will get sent our way for sure.
Interesting
Interesting.
question. Yeah. All right. Next question we have here is, could you let us know how to recommission our contacting and optical extensometers on our 34TM30 tensile tester?
Okay, so it really depends on what extensometers that you have. So definitely reach out after this, let us know what you have so we can give you a more tailored response. But in general, our teams will check things like what connector type do those contacting extensometers have? Clip-ons typically share the same connector and should be compatible with your newer system. For the optical extensometer, we'll need to know first what the device is, what it's mounted on, what version of software you're planning on using. When we release new frames, we do try to ensure that we have some backwards compatibility with older accessories, but nothing is guaranteed, and I don't know how old everything is. So I would say definitely reach out, contact sales or your service rep to learn a little bit more for those situations.
Great. Next question we've got here is, what has been the best practice you have found for dealing with reflective materials being tested with the video extensometer?
Yep. So it depends on what extensometer again that you're using. Maybe Josh can speak to this a little bit after, but the AVE3 has dynamically adjusting lighting. So it'll optimize the amount of light to make sure that you're getting very good illumination of the mark that you have on your specimen. Um, if we're assuming you have an AVE2 that has fixed lighting, so some of my recommendations for you would be maybe slightly adjust your light bar away from the specimen. Maybe that fixed illumination is too bright. Secondly, if your specimen's behaving like a mirror, you could paint the specimen and then apply marks. So then there's not this wealth of light getting reflected back at the device. Um, Something else I'd recommend for you to check is what color are you marking your specimen with? A lot of times when people get the AVE and let's say they're testing aluminum, I see them put black marks on the specimen because it's very obvious the contrast between the mark and the specimen to our human eye. But the AVE has cross polarization built in. So in those situations, marking with a white marker is actually preferred. And if you do that, just throw it in front of the AVE to do a quick check, and you'll be able to see very nice contrast in those situations. So try those things and definitely reach out if you're struggling with anything specific, because our applications team deals with this all the time.
Yeah, I'll just echo what Casey said. We definitely have experienced that. What looks best to the eye is not necessarily what will be giving you the best tracking of the marker with the AVE3. I've had to put white dots on things where black definitely looked like it was the right choice,
Yeah.
but white was would give me a much better data signal.
Yeah. That's usually from customers testing metallic materials. That's something they learn very quickly.
All right, great. We have a few questions that seem to come in that asking like material compatibility. So we'll kind of jump through some of these. So this one is asking about which extensometer types are feasible for fiberglass specimens.
hmm there's definitely a range of what fiberglass specimens look like. Some maybe those reinforced materials that look like traditional dog bones. Um, you could use a clip-on for those. You could also use non-contacting if you're worried about explosive failures, because some of that reinforced composite material can be very strong. If you're testing single strands, depending on how thin your strand may be, a clip-on might not be able to be attached without actually warping the specimen. So in that case, I'd probably recommend non-contacting. And when you are testing single strands, sometimes we see customers attaching styrofoam balls to mark their gauge length. Sometimes we see customers using different types of solutions other than the paint pens that we supply, like nail polish, to make little blobs on the specimen before testing. So it really just depends on what your specimen looks like and what if it can handle any weight being applied to it or not.
All right. Now we have a question about cylindrical samples. Any advice on using AV on cylindrical samples? Is it still able to track dots over a curved surface?
Yep, definitely still able to track dots over the curved surface. It's still going to be calculating and finding that centroid of however you're marking your specimen. So there's not a concern with round specimens.
How about textiles? Can you measure strain on textiles using the AV?
Yep. So for textiles, sometimes we occasionally see customers jumping to digital image correlation because a lot of times those textiles aren't going to break. There's no reduced section most of the time that I see. So they like to really analyze what's happening where post-processing. But non-contacting would certainly be my recommendation for textiles because I think you would have a really hard time, depending on what your surface roughness looked like, getting your knife edges to rest in a nice place with contacting.
Okay. We have a question about aluminum, and I know Josh covered a little bit of oil specimens in his presentation. So for aluminum, is AV3 better than contacting for data accuracy and speed?
It really just depends on what gauge length you're testing to. Our spec sheets are on our website. As far as performance, our extensometers are capable of meeting class B1 for ASTM or 0.5 for ISO. So it's really just your preference, what works best for your lab, what's within your budget. So.
All right. There are a couple other questions that maybe are a little more specific to the use case. So I apologize. I'm gonna send those to Casey afterwards so she can just follow up with you. But I did want to before we wrap up, just take a moment and thank Josh and Covalent for joining us today. This has been really great, and I appreciate the dialogue. And while we have you, Josh, I know you shared a little bit about Covalent already, but I just did want to give you a chance to briefly share a bit more if there was anything else about Covalent's testing services, what sets you apart, just as we have this opportunity here.
Yeah, sure. Thank you, Nick. I do appreciate that. And thank you for the opportunity to, speak to the audience today. I think we got a lot of people online who have some level of interest in mechanical testing. So that's a cool group of people. There's a lot of labs out there that provide, mechanical testing and other laboratory surfaces. One thing I would say that's a little different about Covalent that I want to highlight for anybody out there looking for a partner to work with is, we're very capable and willing to develop custom test methods. We talk a lot about standardized test samples and test methods, but a lot of times you got a piece of something, you need to understand the mechanical properties, and it just doesn't quite fit a standardized test specimen geometry or standardized test method. We'll work with you to figure out a way to execute that test. And we also will support the full workflow. We don't just do the testing. Like I said, we'll develop the method if we need to. We can prepare the specimens. We'll run the testing and acquire the data. We can analyze the data. Depending on how much you want to disclose about your issue, we'll help you solve your problem. And if there's any ancillary analytical services that are needed to help figure out what those mechanical test results mean, fractography, chemical analysis, elemental analysis, we have all that readily available with experts on hand to, give you the information you need to solve your problems. So thank you for letting me share that about our company.
Yeah, no, thank you, Josh. Just a few quick notes before we go. Again, if we didn't get to your questions today, we'll make sure to follow up with you by email, and a recording of today's session will be sent to all attendees. And lastly, a survey is going to pop up once this webinar ends. We would really appreciate your feedback. And a special thank you to Josh and Covalent again for sharing their experience and insights with us. And thank you all for joining us. We appreciate your time. Take care, everybody.